So yeah, so you can just go through this website and you can just play around with the weights and biases, how a neural network approximates an arbitrary function. So one thing to be noted is that UAT does not say anything about the number of parameters. It assures that there is the existence of a neural network which approximate this kind of function. It doesn't say how to learn and what is the number of parameters and what are the values. It doesn't say anything. So SGD is one type of algorithm where we try to approximate this function. Maybe it may not be approximate the actual function, but SGD is one way. So stochastic gradient descent. Okay. Now I will explain Bezier curves. After that, I will take you through the demo of these Bezier curves. So Bezier curves. Okay, before going through the Bezier curves, I'll just ask some questions like, okay, a straight line, right? Straight line given 2 points, x1 comma x1 comma y1 and x2 comma y2. So given any 2 points, can you construct a straight line? Yes. So there are a variety of ways to construct a straight line. So one form is called parametric form of straight line. Parametric form of line. So this, if you guys have taken any computer graphics course in bachelor's or somewhere, you might have came across this kind of functions like parametric form of a straight line, Bezier curves, many types of algorithms. So let's say what is parametric form of a line. It simply says that x equal to, these are the intermediate points. Okay, x is nothing but uh, x2 into t plus 1 minus t into x1, and y is nothing but y2 into t plus 1 minus t into y1. So anyone say, okay, now I have this parametric representation. Can anyone say what happens when t equal to 0 and t equal to 1?
Uh, you have only one of the terms.
Yeah, only one of the term. When we substitute t, it gives the x1 y1, and when substitute t equal to 1, it gives the x2 y2. Okay, and when you vary t from 0 to 1, like t equal to 0.1, t equal to 0.2, and you substitute these values, what you get is the intermediate values. Okay, so this is how what we can, based on the width here, there is a parameter like how much you want to vary the t. So depending on this parameter, you can approximately how much approximately you want to construct the line. Okay, so now Bezier curves, what does Bezier curves do is it tries to construct a curve. Okay, given any 2 points or 3 points, it tries to construct a curve. Like let's say I have given some three points. So we there are other methods like approximating a polynomial function, but these are, I will say, the disadvantage of using a polynomial function. But Bezier curves are like when you given this 4 points or 3 points, we can construct some cubic form which might not go through these points or go through these points. These are called the control points. Okay.
So you use this full control point to
Yeah, yeah.
construct the line, right?
Uh, okay. Here, construct the curve.
Curve. Okay, yes, I mean the curve. Got it.
Yeah,
Yeah.
yeah. Sorry, eraser. Okay. Now, how to construct this Bezier curves? It says some. Okay. Let's say you have. We will construct now a second order polynomial, quadratic polynomial. Okay. Let's say you have x1 y1, x2 y2. These are 3 points, x3 y3. Okay. And you know the parametric form of these two equations. Okay, now what do you do is, you'll let's say this is the, let's say this is the imaginary line. We haven't constructed this line. Okay, now let's substitute equal to some point one. So here you will get this point, right? And from x2 and y2, in between x2 and y2, also you will construct this point for t equal to point one, let's say. Okay, now uh, these are new points. Let's say x12, y12. Okay, and this is another two new point, x23, y23. Okay, now again, uh, in between these 2 points, you have a compute the parametric representation, and for t equal to point one, what is the intermediate point? Let's say it is AB. Okay, this is the, we haven't constructed this line, but we are at this point. Okay, AB. Now vary this t from, let's say, point one, point two, and trace out only this point A comma B. Okay, and it will be something like a curve, cubic curve. You got the intuition, right? What's happening?
So this curve was because so number one, you pick the dots on the line, and then
Yeah, this.
you move those dots and use the this play around with this t, and
Yes,
those
yes,
and form the curve between these two
yes,
lines.
yes.
Am I right?
Yes, true, true, true.
Get
So
it?
we are taking interpolation of interpolated points. So x1, y1, 2 are the interpolation between x1, y2, x1, x2, x2, 3, x, y2, 3 are the interpolation between these 2 points. And again, a comma b is interpolation between these 2 points. And next time what we do, okay, this is the, let's, here, these are the points.
Mhm.
So now we will go here, t equal to point 2. And at t equal to point 2, it's here, but at point 2 it will be here. This is AB. So we trace out this path of this AB. So this is how a quadratic curve is constructed. So so for cubic we will have 4 points. So for that, something like, we have, okay, okay. So for cubic we need 4 points, point 1, point 2, point 3, point 4, and there you will interpolate between these 2 points, interpolate between these 2 points, and interpolate between these 2 points. So it's like a recursive thing.
I see.
Okay.
Get it? Ah,
Yeah. Finally, after you trace this point, you will get something like a cubic form, and these are called the control points. Okay. Now we will see the demo. Like, I hope it will. Okay. How this is constructed? You see, this is the black one is the being constructed, and these are the interpolation among the straight lines. Okay. Something we can play around with this thing like this way. And this another demo. Here we already constructed a bezier curve, and these are called the control points, right? So we can see after by changing the position of these control points how the curve behaves. Okay, and this kind of curves you must have seen in MS Paint, where you draw the curves. Okay, these are called uh, bezier curves. So still, some might feel it kind of confused because of the interpolation over the interpolation over the interpolation. So there is a nice visualization of this, how this constructed on YouTube. You can later follow the video. So earlier we just shown that saw that a Bezier curve. Now let's see. I was saying that we can fit a polynomial, but there is a problem with this polynomial. So curve fitting is the another domain in machine learning, where given some endpoints, some end some endpoints. The goal is like fit a curve exactly passing through the points. In our just general machine learning, we call this kind of overfitting, but in the curve fitting, in the regressions, there's a separate field. So where they want to fit a curve such that it exactly passes through the all the points. So let's say you have endpoints, right? And what kind of polynomial best fits the endpoints? Okay, so the nth order polynomial like fits the points, but it suffers from Runge's phenomena. What does it? Runge's phenomena states that, let's say this is our target function, which is the blue, and the dots are given as the training data. When you use an nth order polynomial, okay, although it fits through all the points, but at the ends there is a wiggly kind of nature. So this is the issue with nth order polynomials. That is called Runge's phenomenon. Instead, now we came across this. Now we talk about the splines. The spline, the term is coined during when they want to construct some boats or something, because boats are, when we design, it's kind of some shape like this, right? So it, for navigation during the time, the splines term was coined and it was used from then on. So what splines is that, instead of fitting a given endpoints, instead of fitting a nth order polynomial, okay, for every intermediate points x1, x2, x2, x3, fit a cubic polynomial. That is called nothing but the spline. Definition of the spline. Let's say x1, x2, and x3. Instead of fitting a nth order polynomial, consider only these 2 points and fit a third or cubic polynomial, something like this. Okay.
And is it possible that the adjacent joint point become non-smooth
Yeah.
or non-differentiable?
Yes, that comes the next point.
Okay.
So yeah, so now we have endpoints, and these are called n minus one intervals. Okay, and these points are called the knots. But the problem, as Rian just mentioned, if we only construct considering these 2 points, and will what do you say, if we build a polynomial, it may not be continuous, right? It's something like this and something like this. There is no continuity, or something like this. There is no continuity. It's not smooth. So we have to also ensure it must be smooth in terms of first order, second order. So okay, now here's a question. You have an nth order polynomial, right? Nth order polynomial with, okay, nth order polynomial, sorry, you have n points and n minus 1 subintervals, and for each subinterval you want to build a cubic polynomial. So any guesses how many parameters we need to find? So okay, so I will break down it. If you want to construct a cubic polynomial, okay, cubic polynomial, how many parameters we require to construct a cubic polynomial? Like coefficients, we need some coefficients, right? Ax cube plus bx square plus cx plus d equal to 0. So these are unknowns, right? So for cubic polynomial, it's 4. Okay. So here there are n minus 1 subintervals. Okay. So it will be 4 into n minus 1 parameters we need to estimate. It's clear, right? Okay. So, but we have only n points but we needed 4 into n minus 1 parameters. So it's like if there is an imbalance between the number of equations and the number of parameters. Okay. Okay, it's the same question. So the care must be taken that let's say this Sx are the third order cubicles. Okay. S1x, like these are the 2 points. Let's say these are the 3 points. This S1x is one polynomial, S2 is this polynomial, and S3x is this polynomial. Okay. So each S1, each polynomial has its own parameters, like A1x cube, and let's say here it is A2x cube in this way. Four parameters. It's its own parameter. The conditions what should ensure is that the adjacent polynomials at this xk plus 1 must be same. Like if let's say this is s1 of x2 must be equal to s2 of x2. So there is a continuity, right? So in this way we get n minus 2 conditions. And we also ensure that the first order derivative also must be equal, and also we ensure that the second order derivative also equal at adjacent points. In this way we get n minus 2 total n minus 3 into n minus 2 plus n conditions, but still there are two conditions left over. What we assume is that at the end points the second order must be something 0. Okay, something 0. So we get exactly 4 into n minus 4 conditions and 4 into n minus 4 equations. We solve it. So here you must have seen the complexity of building a spline with this kind of parameters. So if you when you read the paper of Can, it's the basic building block is B spline, right? And you also came across this term, this uh, observation that it is hard to train, it is taking more time to train. So this is one of the reason, because uh, there are a lot of iterations and uh, intermediate dependency. So that is why it cannot be represented in some linear transform like W transpose X. So our intermediate in this way, that is why it takes more time to compute, learn.
So you are saying each of the spline have to, for each variable needs to build separately. So therefore you cannot do those matrix multiplication to do
Yeah,
that.
that's what I mean. Okay, I'll just go through one more thing. B spline, it is little bit more complicated. Okay, just here it's the same as this thing. If you look at this, our B splines, B splines are nothing but here. This is the spline. B splines are nothing but basis splines. So it's like if you want to compute a spline, you will use some basis spline, something like this, third order. It's a linear combination of these splines. Okay, and how do you compute these splines is it's little bit more complicated. Like look at this equation. See, this is a recursive formula, Cox de Boer recursion formula to approximate this uh, coefficients or anything. So each one is dependent on its lower order polynomial. This is lower order polynomial. This like one if you want to build a third order basis function, it is dependent on the second order basis. It's dependent on the first order basis. In this way, it is recursively dependent on it. So this may be I'm not sure, this may be the cause why it is cannot be parallel. I'm not sure. So,
Hmm.
okay,
So mean,
Dr.
wait,
Dev.
wait, wait. So it means the later spline needs to depend on the previous one.
Yeah, in only one B, yeah, one B spline. If you want to construct a, okay, uh, okay, here this is each one is a spline,
Yeah.
right? And this spline is a linear combination of B splines. And to construct or estimate this B spline, this is recursively dependent. We are talking about only one spline.
Hmm.
One spline. To construct that spline, it is recursively dependent.
I see.
I mean, uh, I have to also look at the code. I also get confused. Like here, I'm not sure. Like, okay, how the control points are being learned, how this code is being implemented.
Mm.
So I'm not sure.
Sure, no problem.
Yeah, yeah. So, so we are can what it says that okay in that paper. Okay, now you got the idea, right?
Yep.
And like let's say again we talk from the okay universal approximation theorem. So when we are using nonlinear activations, right? When you are using nonlinear activation, when we want to approximate this kind of curve, we have only some nonlinear activation like sigmoid or tanh. Okay, we have to manipulate this kind of activation functions into bins such that it fits into this kind of curve. Okay, but what I assume is that, and we need more number of bins to approximate this kind of function such that the width of the neural network is increasing. That is why the weights are increasing, number of weights are increasing here. It's it's a the basis itself the spline. So this is a function and you want to approximate the spline itself has has this some property of some that curvature, right? So maybe this is making it easier without requiring more number of splines, a more number of splines, unlike a neural network, to approximate this curvature. That is why the number of parameters are required for this is lesser than compared to the neural network. That's what my intuition is.
Sure.
Okay. So, and can one also mentions is that this kind of architecture, this kind of neural network, I mean, based on the splines, it's already been used, but they say that they didn't generalize for deep neural networks. So, what they suggest is that it's simple, like composition of composition functions. They say that we can build this thing. What this suggest multi-hidden layer, and they also did lot of experiments and data set and also some proofs which I didn't understand. I want to understand. Yeah. Okay, now we if we look at this each function, this phi. Okay, okay, if you look at this function, there is also some w parameter. Okay, this is a spline which is nothing but the spline is a linear combination of b splines, and bx is some, I think it's silu, which is again a nonlinear activation. So they are using combination of splines plus this nonlinear activation. So these are the learnable parameters. W is the learnable parameters, and splines we have that control points. Okay, the control points are the
Wait,
learnable.
what's this omega or W? Is that metrics or
They say that it's a learnable parameter.
it's a single
Yeah, yeah,
real
single.
number
Yes, yes,
or
single,
oh, okay,
scalar.
okay.
Yeah, yeah. Okay. One more thing, interesting thing is that okay, uh, this phi x, which is a spline, it's a linear combination of multiple splines, right? And this number of splines we can also adjust the number of basis splines.
I see.
Depending on the number of basis splines, the complexity of the model can be changed. And they say that we can see that, I mean intuitively, okay, it's a combination of multiple spines, so must be the final constructor curve. It should maybe little bit more complex, so it can approximate the curvature uh, function better. And one more important thing is that okay, this is coarse grained, like this basis functions are separated, the distance is kind of little bit more compared to the fine grained. Okay, the advantages of a neural network models is that, let's say you want to train a CIFAR10 neural network, CIFAR10 data set, but you started with a 6-layer neural network. Okay, and you achieved only some 85% accuracy, And what is the one way you can do is that increase the number of layers, let's say to 10 layers or 12 layers. Okay, here, but you have to train this 10 layer neural network from the scratch, right? You may not be possible for you to use this 6 layer weights to initialize this 10 layers. So this must be trained from the scratch. But here what they say that you don't have to train it from the scratch. You just have to increase the grid extension from 7 to 12. So in this way you are increasing the complexity. So you initially you train with the 7 bins, and you just have to do some little bit optimizations to adjust these control points, and you can increase the complexity and start training from there. So in this way, the adapting the complexity in CAN is easier than neural network. That's what I understood. And so that is why maybe it is also better for continual learning, I guess. Maybe this is for one task.
Can you repeat that part? So if you already have a new task, you sorry, if you already have a model, you don't have to train from scratch.
Yeah, that's what they say. And okay, what they say is that you can just increase the number of this B splines
Oh, I see.
from
So
uh-huh.
so this is in the case of your new task is uh
Okay,
so
in this,
go
okay,
ahead.
before going to continue learning, just we stick with the simple learning. Where we observed is that okay, we have to increase the number of layers to approximate it better. Okay, but
Mm.
in neural network we have to train it from scratch. Here we don't have to train it from scratch. We just have to increase the number of basis functions, and this CIs, these control points, which are learned, not the control points, sorry, uh, mm, weights. Okay, linear weights, this has to be adjusted, and from there we can continue training. So you
So
don't have to start from the scratch.
so you mean the B actually can be reused, but
Yes, yes,
the
yes.
coefficient of them can be need to be adjusted.
Need to be adjusted. And that is also, they show a simple equation, RMS equation. We can adjust before starting the training, and start the train the model from there.
And that assumption would be useful, I think, if the new task is
Yeah, yeah.
slightly different from the previous one, or it's very if it's completely different. If let's say my new task is a delta function, right?
Mhm.
And,
Yeah, yeah.
would that still work?
Yeah, I mean, not sure, not sure.
Mm.
Yeah, I mean, it still have like, still I got something, but I didn't understand completely. I can't say, sorry.
Okay, I can ask him. I can ask him. No worry. Yeah,
Yeah,
because
yeah,
I know at least one or two member in our team are focused on continual learning. So
yeah,
I
yeah,
it seems to be the result from Ziming is promising, but I can double check with him about the where it can be used. Yeah.
yeah, yeah. Sure, sure. That's nice. Okay, okay. This is the end of the slide. So, yeah, this gives some nice new interpretation of the neural network. I think the power, the representation capacity of CAN and neural network is the same, but it more flexible, I guess. CAN, that's why it's require less number of parameters. That's what I understood. And yeah, and maybe the immediate idea which I got is like, Gaussian process, right? What Gaussian process is does do, it is also a, like, if there are 2 points, so what Gaussian process after computing the posterior is something like, there are many functions which are going through this point, but they are something like this, right? So can we also construct this kind of Bezier curves, because this is also some continuous function which is a Bezier curve. So the idea is like can, or Bezier curves for uncertainty estimation,
Mm.
just like mimicking some Gaussian process, because it also something like fitting curve, but passing through these control points, right? So this is one thought I came to in my mind. Yeah, have to think. Yeah, that's the end of the slides.
Great, that is wonderful sharing, and I saw you get into very detailed information of
Yeah,
the
thank you.
basic math and algorithm. Let's open for function for question. Maybe let me stop recording for now.